Yeah, good evening again. In previous lecture of mole and stoichiometry, we have just finished the basic calculation related to mole concept, in which we have calculated the number of moles, number of atoms, number of particles, and then volume occupied by gas at NTP or STP. Or basically, this is the interconversion between mass, volume, number of particles. We have calculated number of particles in a given mass or the mass percentage. So basically all the thing we have done till now, it is basically calculation of moles, number of particles, mass, or their interconversion. In today's lecture, we'll use the concept of mole during the reactions also. So basically today's lecture is known as stoichiometry. So today's topic of the lecture is stoichiometry. So let's start the topic related to stoichiometry here. So the meaning of stoichiometry. So stoichiometry. The meaning of stoichiometry is calculation based on chemical reactions. Yeah, so the meaning of stoichiometry is it is calculation based on chemical reactions. We'll do three parts mainly. Let's say it's A part, maybe it is basic stoichiometry. Similarly, it's, let's say, B part, apart from basic stoichiometry. Next is, let's say, POAC. POAC. This POAC is principle of atom conservation. Principle of, let's say, atom conservation. And C part, apart from POAC, its C part is limiting reagent. We'll do one by one all three parts, including, let's say, basic stoichiometry, including, let's say, principle of atom conservation, and including, let's say, limiting reagent. So first we'll start from, let's say, basic stoichiometry. And let's say one of the example based on basic stoichiometry is, if any balance reaction is A can combine with 2B, it gives C, let's say. It means, let's say, 1 mole particle of A can combine with 2 mole particle of B, and it can produce, let's say, 1 mole particle of C. It may be atom, it may be molecule, it may be ion, but the stoichiometric ratio, which is the coefficient of multiplication, here stoichiometric ratio is 1:2:1. So basically it is the stoichiometry or coefficient ratio of number of reacting particle to product. We'll do directly questions based on this simple stoichiometry, in which, let's say, question number 1 is, find out maximum numbers. Find out maximum number of moles produced. Find out maximum number of moles produced from 10 moles of A. Find out maximum moles of, you can say, D. D may be another product. Find out maximum number of moles of D produced from 10 moles of A. in given series of reaction. And as per, let's say, question is concerned, the series of reaction may be given as 2A converting to, let's say, 3B, B may be converting to 2C, and 3C can convert into 4D. So I'm repeating my question again. You have to find out the maximum number of moles of D produced from 10 mole of A in given series of reaction. With starting, let's say, 10 mole of A, you have to find out final moles of D. So as per question is concerned, it is 10 mole. Here 10 moles of A is given. So you have to apply basic, basic unitary method. The moles of B produced, from 10 mole. 10 mole of A should be equal to 3 by 2 into 10. It should be same as 15 moles. So as moles of A and B, according to stoichiometry of reaction, their coefficient has to be into 2:3 ka ratio. So from 10 mole, we are getting 15 moles. Again, let's say if we have 15 moles of B, its double mole should be moles of C. So moles of C should be equal to 30 moles. And from 30 moles of C, moles of D produced should be equal to 4 by 3 multiplied by 30, and it should be 40 moles. It should be 40 moles of D. So this 40 moles of D should be my answer. I'm repeating again. Whatever stoichiometric coefficient is given in balance reaction for reactant and product, it is same as their molar ratio also. So from 2 mole of A, you will get 3 mole of B in first reaction. And that's why from 10 mole of A, you will getting 15 moles of B there. Once we get 15 moles of B, the moles of C should be equal to twice of 15, which is 30 moles. And from 30 moles of C, you will get 40 moles of D as your answer. I hope you understood this question. Next question related to stoichiometry. Let's say find out, percentage loss in weight. Find out percentage loss in weight on heating. On heating, it is Na2SO4.10H2O solid. So you have to find out the percentage loss in weight on heating Na2SO4.10H2O solid. So as per answer is concerned, on heating of Na2SO4.10H2O solid, you should know this common reaction. Delta is the symbol of the heat, and on heating this hydrated salt, you will get anhydrous salt and let's say 10H2O vapor. So if you see total mass of Na2SO4 dot, it is basically 10H2O. So total mass of Na2SO4.10H2O should be equal to twice of atomic mass of sodium plus it should be 32 plus 4 times of 16 and plus let's say 10 times of 18, and it should be equal to. So this is basically the total mass of Na2SO4. as per this total mass is concerned, it should be, 46 plus 32 plus 64. So it comes out to be, it is 142 plus 180. So its total mass comes out to be 322. And out of 322, you can imagine 118 gram is lost on heating, and only 142 gram is remaining out of 322 grams. So I'm repeating again, on heating of this hydrated crystal, there is a loss of water of crystallization due to which its mass will decrease. And overall, the percentage loss, percentage loss in weight on heating should be equal to, it is 180 out of 322 into 100. This will be the percentage loss on heating, and it comes out to be 180 multiplied by 100 and divided by 322, and comes out to be around 55.9%. I'm repeating the question again. You have to find out, percentage loss in weight on heating of Na2SO4.10H2O solid. So we know on heating of this salt, there will be 180 gram of H2O vapor is lost. It is escaped to atmosphere on heating 322 gram of the salt. So the percentage loss in weight on heating is 180 out of 322 into 100, and it comes out to be 55.9%. Okay, next one. Let's say question number 3. Find out, volume. Find out volume of oxygen gas required at NTP for, complete combustion. For complete combustion of, you can say it is 29 gram of, let's say, LPG, which mainly consists, you can say, butane. You have to find out the volume of oxygen gas required at NTP for complete combustion of 29 gram of LPG. LPG, let's say, mainly consists butane. Here, as per question is concerned, you can imagine it is 100% butane. To see its answer, let's say, as per butane is concerned, it is C4H10. Butane. And the meaning of combustion is its reaction with oxygen can give CO2 and, let's say, H2O. To balance this reaction, you have to multiply it by 4. You have to multiply H2O by 5. And overall, as per oxygen coefficient is concerned, it is 8 plus 5, it is 13. So it is 13 divided by 2. So the balance reaction for 1 mole. As per C4H10 is concerned, from here you can simply say it's 1 mole required 13 divided by 2 moles of O2 for complete combustion. It's 1 mole mass is 58 gram. So it's 58 gram required 13 by 2 moles of O2, and as per question is concerned, it is 29 gram. So, for 29 gram, which is just half of 58, fortunately, it is 13 divided by 4 moles of O2 is required. It is 13 divided by 4 moles of O2 is required for complete combustion of 1 mole of butane. From here, it is volume. It is volume of O2 at NTP should be equal to, it is 13 divided by 4 multiplied by volume of O2 at NTP means it is multiplied by, let's say, 22.4 liter. We already know volume occupied by 1 mole of gas at NTP is 22.4 liter. The same calculation we have done in the last lecture also. So it is basically 13 divided by 4 and multiplied by 22.4. So it comes out to be 72.8. 72.8 liter of O2. So as per question language is concerned, I am repeating again. First, we have just calculated how much moles of O2 is required for 1 mole of C4H8 combustion. 1 mole of C4H10 weigh 58 gram. So for 58 gram, if we require 13 by 2 moles of O2, so for 29 gram, we require 13 by 4 moles of O2. Volume of O2 at NTP should be equal to 13 by 4 into 22.4 comes out to be 72.8 liter of O2. I hope the question makes some sense. Through this type of calculations, we can find out the mass, volume of other reactant, other product, if mass or volume or moles of certain reactant or product is given. Let's say I can just make one more question. Question number 4. Let's say if 1 mole of iron, Fe, the symbol of iron, if 1 mole of iron can completely react with 0.65 moles of oxygen and produces mixture of FeO and Fe2O3. If 1 mole of iron can completely react with 0.65 moles of O2 and produces mixture of FeO and Fe2O3, then find out moles of FeO and Fe2O3 produced. You have to find out the moles of FeO and Fe2O3 produced. So to do the question, you have to write obviously the balance reaction between Fe and oxygen. So one of the reaction may be iron when react with oxygen. Iron when react with oxygen, it can give FeO. So as per question is concerned, it is iron can react with O2 and let's say it can produce FeO, and simultaneously iron when react with O2 it can produce Fe2O3. In balance reaction you have to multiply O2 by 3 by 2 and then it is 2 Fe. Overall, as per moles is concerned, let's say moles produces for FeO, you can imagine it is X mole of FeO produced and let's say Y moles of Fe2O3 get produced. The point is, as per question is concerned, you have to just find out the value of X and Y. So you have to find out the moles of FeO and Fe2O3. So your purpose of this question is you have to find out the value of X and Y. So Fe plus half O2, it will give FeO. 2 Fe plus 3Y2O2 will give, let's say, Fe2O3 here. If we have, let's say, X mole of FeO, it should be X mole and it should be XY2 moles. From here, it is 2Y moles and it is 3Y2 moles, let's say. So for X mole of FeO and for Y moles of Fe2O3 respectively. Now, as per total moles of iron is concerned, total moles of Fe get consumed. Iron get consumed should be nothing but X plus 2Y, and X plus 2Y should be equal to 1. As per question information is given, it is 1 mole of iron. Similarly, the moles of O2 get consumed. Moles of O2 consumed should be equal to, it is 2Y. So it is moles of O2 get consumed is XY2 plus 3Y2, and it should be equal to, let's say, 0.65. Here you can simply say X plus 3Y should be equal to, let's say, 1.3. Here we have two equation, ये equation 2 है, and let's say ये equation 1. Equation 1 and 2. So total moles of iron get consumed is X plus 2Y should be equal to 1. And moles of O2 get consumed should be equal to, let's say, X plus 3Y should be equal to, let's say, 1.3. Two equations, two variable here. One is X plus 2Y equal to 1. Another is X plus 3Y equal to 1.3. So if you solve these two equations, Y ka value you will get 0.3 and X ka value should be equal to, let's say, 0. So Y, you directly subtract equation 1 from equation 2, you will get the value of Y. And as per X ka value is concerned, how much X ka value you will get? It is, let's say, 0.4. So moles of FeO, which is X, should be equal to, let's say, 0.4 moles, and moles of Fe2O3 produced, which is Y, comes out to be 0.3 moles. So mainly as per the stoichiometry is concerned, obviously you have to just write their balance reaction first. Apart from balance reaction, you have to just cross check how much moles of different reactant get consumed and how much moles of product will be produced depending on the stoichiometry we have. I hope this question is done. Now let's move to the next one. Next concept. One is, let's say, it is POAC. As per POAC is concerned, it is, principle of atom conservation. Principle of atom conservation. It is nothing but actually balancing of redox reaction only, a balancing of reaction only. Principle of atom conservation. So in any chemical reaction, total atoms of given element, in any chemical reaction, total atoms of given element will be, conserved. In any chemical reaction, total atoms of given element will be conserved. Obviously, carbon will remain carbon, the nitrogen will remain nitrogen, oxygen will remain oxygen. So in principle, total atoms of a given element during any chemical reaction will remain same. It is practically balancing of redox reaction only. So if you see one of the particular situation, for example, in a given test tube, let's say if we have 8 grams of sulfur. Now, if the sulfur, in a given test tube, let's say we have 8 grams of sulfur, the sulfur is treated with, excess of oxygen such that all its sulfur on burning, let's say, produce SO2 gas. Further, SO2 gas may be treated with chlorine water Cl2, and Cl2 can oxidize this all SO2, let's say, into SO3. This SO3, when treated with, let's say, H2O, suppose as per reaction information is given, let's say all this get converted into H2SO4, and when this H2SO4 treated with, let's say, ferric hydroxide, here in the question it is given as, let's say, it get converted into ferric sulfate. Now the typical question may be, find out the mass of ferric sulfate produced. Find out, mass of ferric sulfate produced from, 8 grams of sulfur in given series of reaction. So the typical question of principle of atom conservation, POAC, from 8 grams of sulfur, let's say how much mass of ferric sulfate get produced. Now, there is no need to find out the mass of intermediate product, including SO2, SO3, and H2SO4. If you know, sulfur will remain sulfur throughout. So whatever moles of sulfur, whatever moles of sulfur present in first test tube, the same sulfur moles will remain in second tube also. Same moles of sulfur will remain third tube, fourth tube, and let's say the same eventually. So same sulfur will remain, as sulfur moles will remain constant. The same concept of POAC. So whatever moles of sulfur present initially, it is the sulfur ke moles finally also. So initial moles of sulfur, initial moles of sulfur, initially moles of sulfur should be equal to, final moles of sulfur. Initial moles should be equal to, let's say, mass divided by its atomic mass, which is 32. and should be equal to, let's say it is nothing but mass of Fe2SO4 whole thrice divided by molecular mass of ferric sulfate. If you add iron, let's say it is twice of 56 for iron, and it is thrice of 96. Overall it comes out to be, let's say, 400 as a molecular mass of ferric sulfate. So this is nothing but the moles of ferric sulfate, mass divided by molecular mass, and every moles of ferric sulfate consists three atoms of sulfur. It is three atoms of sulfur. So I'm repeating again, 8 divided by 32, which is nothing but number of moles of sulfur, should be equal to mass of, let's say, ferric sulfate divided by its molecular mass. And it should be, let's say, 8 divided by 32 should be equal to mass of ferric sulfate. Let's say, suppose it is x gram divided by 400 multiplied by 3, and from here x comes out to be, let's say, 400 into 8 divided by 32 divided by 3, 8, and it is 4, and it is 100. From here it comes out to be, let's say, 100 by 3, and this x ka value comes out to be 33.33 gram. So I'm repeating again, here there is no need to find out the mass of every individual intermediate. If we know sulfur, moles of sulfur will remain sulfur only. So you can just find out initial moles of sulfur, and you can just find out final moles of sulfur, and then you can just equate. Similarly, let's say another question based on POAC. If it is given in the question, 27.6 gram of K2CO3. 27.6 gram of K2CO3 on reaction with series of different reagent. .6 gram of K2CO3 on reaction with series of different reagent get converted into let's say it is K2ZN3 FeCN6 whole 2. This is something complex compound. So if 27.6 gram of K2CO3 on reaction with series of different reagents get converted into, so it is get converted into K2ZN3 FeCN6. So from where the zinc comes, zinc or iron. Let's say once we said different reagent. So from different reagent, we can have zinc or iron there. Such that all atoms of carbon get converted into product. Such that all atoms of carbon get converted into product, and you have to, let's say, find out moles of final product K2, and it is Zn3 FeCN6 whole twice. So you have to find out the moles of, let's say, K2 Zn3 FeCN6 from 27.6 gram of K2CO3. So as per information in the question is given, it is K2CO3 when treated with series of different reagent. It is treated with, series of different reagent. It may be anything, including they containing zinc, including they consist iron, but the condition is all the carbon get converted into this complex product. It's all carbon get converted into this complex product. Now, since as per question is concerned, it is given as 27.6 gram. And let's say, suppose if we have X mole of this compound, as per information in the question is concerned, you have to find out the value of X. As per information in the question is concerned, you have to find out the value of X. Let's say as per K2CO3 is concerned, its molecular mass should be equal to, it is, let's say, twice of 39 plus, it is 12 and plus 3 times of 16. So as per molecular mass, of this compound is concerned, so it is 78 plus 12, and it comes out to be 48. So it is 90, and overall it comes out to be 138. Molecular mass of K2CO3. So as per moles of K2CO3 is concerned, moles of K2CO3, which is 27.6 mass given divided by its molecular mass, it comes out to be 0.2 moles. And whatever we have moles for, K2CO3, we should have same moles as carbon also. As per molecule, we have one atom. So moles of carbon atom should also be same as 2. According to POAC, Principle of Atom Conservation of Carbon. Finally, product also consists, moles of carbon as 0.2. Every molecule of this complex compound consists, 12 moles of carbon. Every moles of, let's say, this complex compound consists 12 moles of carbon. So this multiplied by 12, X, which is the number of moles of this complex compound, multiplied by 12 will be the moles of carbon, and this moles of carbon should be equal to 0.2. From here, moles of this complex compound, moles of K2Zn, it is, let's say, X comes out to be, it is 0.2 divided by 12. So it comes out to be, let's say, 1 divided by 60. So 1 divided by 60 moles. I hope it is clear the meaning of POAC. So I hope you are getting the same concept, which is known as Principle of Atom Conservation, POAC. In the case of POAC only, here the next concept apart from POAC, it is, limiting reagent. Limiting reagent. So as per limiting reagent is concerned, in any chemical reaction, if particular reactant get consumed or exhausted completely, in any chemical reaction, if particular reactant get consumed or exhausted completely, it is known as limiting reagent. It is known as limiting reagent. Or you can say any reactant which get consumed first. Consumed first is limiting reagent. Limiting reagent consist minimum moles per stoichiometric coefficient. Any reactant get consumed first is known as limiting reagent. Limiting reagent consist minimum moles per stoichiometric coefficient. And one more point you can write, limiting reagent will decide the amount of other reactants get consumed or it limit amount of products. It limit amount of product. Here I'm repeating again, in any chemical reaction, if particular reactant get consumed or exhausted completely, it is known as limiting reagent. Any reactant get consumed first is limiting reagent. Limiting reagent consists minimum moles per stoichiometric coefficient. Limiting reagent will decide the amount of other reactant get consumed or it limit amount of product. To understand the definition of limiting reagent in detail, I can take few examples here. I can take few examples here. As per examples are concerned, I am just sharing few pics related to this. Let's say one of the example is, it is limiting reagent. So one of the simple thing is, let's say how many complete car can be prepared from You know, how many complete car can be prepared from, you know, if we have 8 car bodies as this, and let's say we have 48 tires, 48 wheels we have. So if you see the balance reaction here, you can say it is, let's say, car bodies, they need, let's say, 4 tires, and it will be, let's say, you know, full car, one full car. So it is 1:4 car ratio. So if we have eight car bodies maximum, they required 32 tires. Maximum they required 32 tires, 8 multiplied by 4, and we have 48 tires. So confirmly 48 tires is found to be in excess, and the limiting reagent is going to be this car bodies. So it is nothing but, you know, limiting reagent. Their limiting reagent is going to be these car bodies. 48 tires, out of 48 tires, 32 tires get consumed, and you know, 48 minus 32 which get consumed, 16 tire will be in excess. So limiting reagent is going to be here, let's say, car bodies. Reaction end, when one reactant is totally consumed, this is the limiting reagent which get consumed completely. The other reactant are excess reactant, and other reactant will be remaining in certain amounts. Stoichiometric relationship apply only to the amount of the substance consumed or, you know, produced in a reaction. Select a product and calculate the moles from each reactant, assuming it is completely consumed. The limiting reagent, the limiting reactant yield the fewest moles of product. Obviously, let's say, since it has minimum moles per stoichiometric coefficient. I hope through this picture you will get some idea related to limiting reagent. I'm sharing one more related to limiting reagent only. Let's say another pic related to limiting reagent to understand the limiting reagent. Here we have 3 things to have complete bicycle. You have obviously wheels, tire, you have bicycle body, and then you have, you know, axle and chain, pedal and chain basically. So again, if you see the balance reaction here, if you see corresponding symbol for wheel, I can put, let's say, W here. You know, it is bicycle body, and you know, pedal and chain, let's say, P here. So to get complete cycle, you have 2W plus, you know, 1 body plus 1 pedal and axle. You will get complete bicycle. You will get complete bicycle, or you can get, let's say, complete cycle, bicycle. Now to check the limiting reagent here, let's say, as per wheels are concerned, 1, 2, 3, 4, 5, 6, 7, 8. We have just 8 wheels, and obviously it can form only 4 cycles. We have 5 bicycle bodies, and thus obviously 1 extra body can be remaining, and let's say 5 paddle wheel also, and again 1 paddle wheel is remaining. So as per limiting reagent is concerned, in this case also limiting reagent is going to be this wheels. The wheels is going to be limiting reagent. It will decide how much complete bicycle can be prepared. So from, let's say, 8 wheels in bicycle, you can get 4 bicycle complete. I hope now you know better visualization of limiting reagent concept. Now to do few numericals based on limiting reagent, I can take few 3 to 4 examples related to limiting reagent calculation. The first one is, that's the first question related to limiting reagent. Find out, maximum moles of C. Find out maximum moles of C produced on, let's say, reaction between 2 moles of A and 3 moles of B according to, let's say, according to reaction is given as it is A plus 2B gives C. Find out maximum moles of C produced on reaction between 2 moles of A and 3 moles of B according to given reaction. A plus 2B gives C here. So first, let's say you have to find out the limiting reagent as per, let's say, stoichiometry of A, B, and C is concerned. It is 1:2:1. It is, let's say, 2 moles of A, and here it is 3 moles of B. Obviously, C is found to be 0. So here you have to first find out the limiting reagent out of A and B. Just think which one should be the limiting reagent out of this, A or B. I hope with 1 mole of A, you require double mole of B. So with 2 moles of A, you required 4 moles of B. So B is found to be in deficiency. So B should be the limiting reagent here, and B should be completely consumed in this case. Out of, let's say, 2 moles of A, according now you can use unitary method. Moles of C produced should be equal to, let's say, 3/2, and moles of A remaining out of 2 mole, 3/2 moles of A get consumed. Moles of A remaining should be half, and moles of C produced should be equal to 1.5. So as per question is concerned, first we have to decide, let's say, A will be the limiting reagent. A or B? B. B is going to be limiting reagent, which is completely consumed. So if you see final calculations also, final moles of B become 0 and still A and C is remaining here. So B is limiting reagent. B is limiting reagent, and maximum moles of C produce. Maximum moles of C produced should be 3/2, or you can say it is 1.5 moles. So you have to find out, let's say, maximum moles of C produced on reaction between 2 moles of A and 3 moles of B according to reaction. A plus 2B gives C, 2 mole of A, 3 mole of B, and eventually maximum moles of C produced should be equal to 3/2 or 1.5 moles. We'll do more questions related to limiting reagent. Let's say another one. Let's say find out maximum mass of CO2 produced on burning of 24 gram of carbon with it is 32 gram of oxygen. You have to find out, let's say, the maximum mass of CO2 produced on burning of 24 gram of carbon with 32 gram of oxygen. Here, as per reaction is concerned, obviously, as per reaction is concerned, it is carbon has to combine with oxygen and it can produce CO2. Now, as per stoichiometry is concerned, is simple. It is 1:1:1 ka ratio, and 24 gram of carbon is given, 32 gram of oxygen is given. It is given as mass. You can find out their number of moles also. So its number of moles is found to be 2 moles. Its number of moles is found to be 1 mole. So here it is easy to guess which one is the limiting reagent. Limiting reagent is found to be O2, as it consists less number of moles, minimum moles per stoichiometry basically. So as per O2 is concerned, it is going to be limiting reagent. O2 is going to be limiting reagent, only it's 1 mole. And carbon is found to be in excess. So as per final moles are concerned, its mole remaining will be 0. It will be completely consumed. And since it is 1:1:1 ka ratio, moles of CO2 produced is going to be 1 mole. And out of 2 mole of carbon, 1 mole get consumed. And in the case of carbon also, only 1 mole of carbon is remaining. So maximum mass of CO2, maximum mass of CO2 produced, maximum mass of CO2 produced should be equal to 1 multiplied by 44 gram, and the mass of CO2 comes out to be 44. I hope this is another question of limiting reagent. More questions related to limiting reagent? Next one. It's question number 3 related to limiting reagent. Find out maximum moles. Find out maximum moles of calcium phosphate produced. Find out maximum moles of calcium phosphate produced on reaction between let's say 0.2 moles, or you can say 0.3 moles of Na3PO4 and 0.2 moles of CaCl2. So find out maximum moles of calcium phosphate produced on reaction between 0.3 moles of Na3PO4 and 0.2 mole of CaCl2. So as per reaction is concerned, this reaction is going to be, it is Na3PO4 when combined with CaCl2, and this produce Ca3PO4 whole twice, and let's say it is NaCl. As per reaction is concerned, to balance, it is 3 here. So it has to be first, let's say 2 here, it is 3 here, and 6 here in the balance reaction. As per Na3PO4 is concerned, it is given as 0.3 moles. It is given as 0.2 moles. It is 0 and 0. So 0.3 mole, 0.2 mole, 0 mole, and 0 moles. As per limiting reagent is concerned, which has minimum moles per stoichiometric coefficient. So I'm repeating again. Limiting reagent consists minimum moles per stoichiometric coefficient. So if you see minimum moles per stoichiometric coefficient, we have for CaCl2 0.2 divided by 3, and thus CaCl2 is going to be limiting reagent here. CaCl2 is going to be limiting reagent. Limiting reagent will completely consumed, so its final moles will be 0. And limiting reagent will decide how much amount of calcium phosphate will produce and how many moles of sodium phosphate will consume. So from 3 moles you are getting 1 moles. So from 0.2 it should be 0.2 divided by 3. From 3 moles you are getting 6 mole of NaCl double. So you will get 0.4 moles. From 2 moles of Na3PO4, or you can simply say from 3 mole you are getting 2 moles with Na3PO4. So its moles remaining should be out of 0.3 moles. 0.4 divided by 3 moles get consumed. So as per moles of calcium phosphate is produced, as per moles of calcium phosphate is produced, this is the maximum moles of calcium phosphate, and thus this should be our answer. Okay, I can do one more question related to limiting reagent. So in this question again, so one of the easy trick to find out the limiting reagent is it should consist minimum moles per stoichiometric coefficient. I can just elaborate the same thing in another example. Let's say it is example number 4. It is 2A plus 3B plus C should convert into 7D, suppose. And initially, let's say at T equal to 0, its moles is given as half mole. Its mole is given as, let's say, 1/3 moles. This moles is given as, let's say, 7/2 moles. It is initially 0. So if we have to find out the limiting reagent, so limiting reagent is, let's say, you can first find out moles of different reactant, per stoichiometric coefficient. Here it is, half divided by 2 for A, and which comes out to be 1 by 4. Similarly, let's say for B, it is 7 by 2 divided by 3, and it comes out to be 7 by 6. Similarly, for C, it is 1 by 3 divided by 1, and it comes out to be 1 by. Now, out of, let's say, 1 by 4, 7 by 6, out of 1 by 4, 7 by 6, and 1 by 3. I hope 1 by 4 is least. And again, as per definition of limiting reagent is concerned, whichever has minimum number of moles per stoichiometric coefficient is going to be limiting reagent. So can you suggest me out of this A, B, and C, which one is the limiting reagent here? It is A, which has minimum moles per stoichiometric coefficient. So if you see, finally, let's say even at T tends to infinity, on completion of reaction, A, which is limiting reagent, you will get it as 0 moles. The moles of B remaining should be equal to 7 by 2 was initial number of moles, and how much get consumed with half mole of A. It is 3:2 ratio. So it is, let's say, it is 3 divided by 2 multiplied by half. Unitary method. Moles of C, initially it is 1 by 3, and let's say it is half of half get consumed with half moles of A, and moles of D get produced should be equal to 7 divided by 2 times of half is the moles of D which get produced. So if you do calculation further, A eventually it is 0, and it is 7 by 2 minus 3 by 4 is 14 minus 3. So you can say it is 11 divided by 4 moles. Similarly, it is 1 by 3 minus 1 by 4. It is 1 by 12. 1 by 12 moles. Similarly, it is, let's say, 7 by 4 moles of D get produced. So if you see in today's lecture, as we have target to do basic stoichiometric calculations, till now we have understand how to do the basic calculation related to mole concept if reactions are concerned. In today's lecture, we learn the concept of POAC, which is principle of atom conservation. And in today's lecture, we learn the concept of limiting reagent. So as per stoichiometry is concerned, you have to do lots of practice from here. So as your practice will increase, you will get more and more confidence in doing these type of problems. But just remember, as per this mole concept or basic stoichiometry is concerned, it is basic fundamental of all the calculations we are doing in math and chemistry, basically, particularly. So, for example, in chemistry, we'll do few chapter including chemical equilibrium, ionic equilibrium, thermodynamics, liquid solution, solid state. All these are the backbone of physical chemistry of class 11th and 12th. Everywhere we require basic knowledge of mole and stoichiometry. So just do practice related to moles and stoichiometry from your class 11th standard book. It is obviously irrespective of your board. It is going to be first or second chapter of your class 11th textbook. Solve from the textbook only. So in the next lecture, we'll do the last part of mole and stoichiometry, which is concentration term, including molarity, molality, mole fraction, all these things. Okay, I'm going to finish this lecture now.